Alright, hello everyone, welcome back to Friday Night Physics. This is the second episode. Today we're still going to continue with dynamics. Last week we were just focusing on inclines, but this week we're focusing more on different other categories of dynamics. And the basic prerequisites, I didn't erase it, it's still the same. It's just Newton's 3 laws and basic kinematics and dynamics and like knowing about friction and stuff. So without further ado, let's move on to the first problem. The first problem says a 5 kilogram ball is dropped from a 3 meters tall building and falls into a 1 meter of snow before coming to a stop, and find the average retarding force of the snow. And you have G is equal to 10 meters per second squared, as always with the USA FO. Sorry, F net equals MA. Well, both of them have G equals 10 meters per second squared. And so for this problem, what you want to do is, as for any dynamics problem, you want to be able to know what forces are in action and which forces act in opposite directions and such. But first, if we just first apply basic kinematics, the velocity when it reaches the snow is equal to, let's just call it V final squared. It's going to be equal to, it starts from S, so 0 squared plus 2 times G, which is 10, times the height, which is 3, and that equals 60. And the acceleration required, the deceleration required for the snow to be able to stop it within 1 meter is 0 squared equal to V final squared, which is 60, plus 2 times A times 1 meter. And we have that A is equal to negative 30 meters per second squared. However, you also need to consider gravity as a force, since it's still falling when it's in the snow. So the average retarding force will have to be both of these, including gravity. So it's negative 30 plus negative 10, which is gravity, times 5, which is the mass of the ball, which is equal to negative 200, which is, like, we want to find the magnitude, so it's 200 newtons for the first problem. And so this problem is pretty basic. You just apply the principles of freely falling objects and some basic kinematics. Alright, problem 2. Problem 2 states, Problem 2 states that you have two boxes with mass M1 and M2, and they're attached to a ceiling with a string, well, two different strings actually, and you have that M1 is equal to 2 times M2, and here, let me draw this out, and we want to find when the top string is detached, the acceleration of each block. So you have M1 and M2. And so what we want to do is T1 and T2, these are tensions of these two strings. So we know that T1 has to support both of their masses, so it's equal to 3 M2 times G, the force of gravity, and T2 only has to support M2's mass, so it's equal to M2 times G. And you can find that the net force on the first block is the tension, so it's 3 M2 times G is equal to 2 M2 times A. So the acceleration for A is going to be equal to 3 halves times G, and since G is just equal to 10, it's going to be equal to 15 meters per second squared. And for the second block, the net force on it is 0, so its acceleration is also 0. So let's call this A1, the second one A2, and its acceleration is 0. And again, this just applies basic dynamics and just, Newton's third law, Newton's 3 laws and such. And yeah. Oh, and also, if you don't know any of the basic prerequisites, again, just go to Khan Academy, read a physics textbook or something, and then watch this video, since this is like a problem-solving based series, not like a teaching one. It's more like teaching you how to solve these problems, and the basic concepts will just be lightly gone over. Okay, so next one is a scale is held with both hands. So let's say we have a scale. Let's draw it like this. And then you have both hands. So for example, if I just take my tuner, you have it like this. And then the weight of the scale is 5 kilograms. 5 kilograms. And one hand exerts a force upwards with magnitude 200 newtons. Find the scale reading. So we know that the lower force is going to be equal to the force of gravity. Well, the force of gravity is just 50 newtons, and so we know, since like the hand on the bottom pushes it up with 200 newtons, the hand on the top has to push down and balance it. And so that means that the force exerted by the the top hand is going to be 200 minus 50, which is equal to 150 newtons. And it says we want to find a scale reading, which is basically its weight. And so that's just 150 newtons divided by G, which is just equal to 15 kilograms. And and the scale reading is just what the scale states, like if you like your bathroom scale. Okay, and the next problem says that, let me move on to the next page. Okay, the next problem states a rope with mass M and length L is put on a pulley such that both ends are even. So like at the same height. And then the rope is pulled down on one end by a length x, and we want to find the instantaneous acceleration when it's let go. So pulled x, find instantaneous acceleration after release. And we also know that this rope or string, whatever, has equal density. So like for a portion that's 1/4 of the entire length, it's going to have 1/4 of the entire mass. So we know, and using this, we know that since you pull on one end a length x, the other end is going to go up x, right? Since the string isn't going to stretch or anything. So we know the net force is going to be equal to 2x, which is the change divided by L. So that's 2x is the portion that has been changed, and L is the total length times M, which is the mass of the rope, times G. And 2x divided by L is just the proportion of the rope. And this is equal to M times A. So A is going to be equal to 2xg divided by L. And yeah, simple as that. That's the answer. So for all of these problems, you'll notice that I just use very simple concepts. Like you can learn these in a physics textbook or Khan Academy or whatever. But the important thing is being able to know which forces are in action and how to apply each force. And so yeah, that's it for this video, the second episode of this series. Thanks for watching. Please consider liking and subscribing and sharing with your friends. Alright, thank you.